Bem-vindos ao Type Theory for All podcast. This is your host, Pedro Abreu, and in this episode is about the journey of a programmer that converted himself into a Haskell developer after working with C and C++ for more than 10 years. What does he find so compelling about Haskell? Why did it make him dive deeper into theoretical computer science? Why did it make him learn Coq and Category Theory? How hard was this transition? Join us in this episode to find the answers to these questions and many others. Let's get into it! Hello everyone, welcome to the Type Theory for All podcast. This is your host Pedro Abreu, and today is my great pleasure to be interviewing John Wiegley. John Wiegley went to George Mason University and he has extensive experience developing with C++. He's been a member for the C++ committee for many years. He then migrated to start working with functional programming and started doing some formal verification. He also contributed to some packages for Emacs. And nowadays he's working on Definity on some blockchain related work. Welcome, John Wiegley.
Thank you, Pedro. Nice to be here.
So, John, as we were talking right before we started this, I was asking if you actually completed your degree in George Mason University.
No, I didn't complete it there. I only did half of the required credits. When I went to school, I did first start out in computer science, but a lot of it was familiar to me from things I'd been doing at home. I now have learned that there is way more to computer science than I was ever aware of back then. So I believe that in retrospect, I made a mistake by doing this. But I kind of wanted to branch out and do some things and learn some things I hadn't been exposed to before. So I switched my degree over to philosophy, but didn't really just take philosophy classes. I was taking classes all across the board: psychology, history, writing. And that's why, even though I had 4 years at the university and a lot of credits, very few of them applied towards my actual degree. I think I only got halfway towards the full degree. And over the course of that time, I was working as a programmer as well. Throughout the whole 4-year period, I would be 1 semester on, 1 semester off, working in the summers. And the work I was getting kept getting more interesting, more lucrative. And I started to wonder, well, why am I continuing this education when I can be in industry? A lot of what I've learned about formal verification and functional programming in the last several years has really opened my eyes to the aspects of computer science I missed because I didn't get deep enough in to see them during those early years.
Oh, wow. So in these early years, in your first few jobs, you were working with C++?
I started out, my first paying job was, believe it or not, in BASIC.
Oh, wow.
And then quickly switched to C. It wasn't C++ for quite a while. I think it took 10 years before I had a job where I actually worked in C++. Most C++ compilers are written in C, so I stayed in C for a really long time. And I found that when I was doing either professional work or in that first 1 year of coursework at the university, it was just programming. It was just telling machines how to do things, which is very imperative in its focus. It's very much about data structures and manipulating I/O and writing programs that are almost like treating the computer as a machine and you're giving it instructions on how to do different things. It really was not about the manipulation of ideas, modeling abstract concepts, exploring thought and new designs.
Right. So you're working on some C++ compilers.
I had a friend who worked at Borland.
Mm-hmm.
He told me there was a job opening in their compiler team. I jumped on that because even in the early days, I knew I wanted to end up either being a compiler writer or someone who worked on operating system kernels. And it was going to be whichever of those opportunities I could find first. So this friend had an opening in the compiler team at Borland, where Borland C++ at the time was very popular and well used. So I joined that team and worked for the first year only on the linker, kind of earning my chops in the team as an engineer. And then I switched to working on the front end, where I stayed for several years. And that encompassed a lot of the years I was in the C++ standards committee while working on that C++ front end.
You said that you already knew that you wanted to be a compilers person. What was so interesting about doing compilers for you?
I think it was just because I had an affinity always for system side programming, more libraries, more algorithms, stuff behind the scenes. And I knew that compilers and operating systems were kind of the two hardest things that I was aware of. So that's why I wanted to do one of them. I wanted the most challenge.
God, I've done when I was an undergrad, I've done a little compiler in C, and it's if you do an interpreter in Haskell or something that has say pattern match, you go back to C where you don't have any of those nice features. It's just so painful.
Yes,
How
it
did
sure
you
can
enjoy
be.
that?
Well, it was the time, right? I wasn't used to having parsing libraries. I didn't know what combinator parsing was. I didn't really have a lot of background in AST based evaluation. A lot of what we did, even at Borland, it was single pass character stream to assembly code, all in one pass.
Wow.
Maybe there was an AST to represent expressions within the function body, but there was not an AST to represent the whole translation unit before compiling it. So I'd say things were more close to the metal back then. Now working in Haskell, sure, same as you. I'm used to very multi-pass compilers where you can debug and analyze the correctness of every phase independently. It's wonderful work now.
I'm sure you learned so much back then.
Oh yeah, definitely.
So
And
you
it set me up to appreciate some of what functional programming offers.
Yeah, I imagine that's really true. So you mentioned that you were also in the C++ committee for quite a while. What is that? What is the C++ committee?
So a standards body, and this was with the ISO organization, and it had been structured such that the ANSI component, which is the US standards body, and the ISO component, which is the international standards body, they were fused. So meeting at one was a meeting of both for that particular standards group, although ANSI would have its own like tiny little sub meeting at some point during the week. But generally you would go to an offsite location that was rotated around the world and meet for 1 week with colleagues, maybe anywhere between 80 to 140 people. And different people had different areas of the language standard that they were experts in, and issues would come up. Either vendors would notice things that were missing from the language that they needed, or users would put in what were equivalent to issue requests, or people just had ideas of features they thought would be useful for the community. Educators too would come and present their ideas. And then it was up to the committee to assess the idea and find out, is what they're asking for, does it make sense? What's the most effective way to implement that as a part of the language? Would this feature be compatible with all other aspects of the language? And what work are we imposing upon implementers if this feature gets included? So each one of those steps required certain expert opinions and background and experience to determine, is this going to be a good idea? Should this be added to the C++ language? Some features that seem at first blush to be like, very easy, they're not going to be a huge impact on the language. When you get deep into how they interact with either inheritance or templates or how expressions, how value conversions happen, for example, because you can have implicit value conversion in C++, you start to find that in the very corners, there are a lot of tricky bits that you have to get right. And you have to spell it out in the standard clearly enough so that when the implementer is done at the end of the day, what they have come up with will render programs into the right result.
And then who gets to implement these features? Because I know that Rust, for example, we have the Rust Foundation where they can hire developers and all of that. How does it work in C++?
C++ is a bit different than a language that was headed by a single organization the way Rust was with Mozilla, or that has a single compiler implementation the way Rust still does today. In the C++ world, the committee was more about the language, not at all about the implementation. Although, of course, we considered the desires and the work being imposed upon implementers. Implementers each had their own compiler because they had their own communities, their own users. Not all compilers implemented the exact same flavor of the language either. That was something that over time got better and better, to where nowadays, if a compiler says that it supports C++ 17, for example, it's very likely that that interpretation of C++ is going to be close to other compilers. Standardization, I think, has become a lot more important over time. But at any one given time, there might be 20 different C++ compilers, some of which were entirely internal to certain companies. So the outside world never used them or never
Right.
saw them and didn't know they existed, but they were still important to the part of industry that that company addressed.
Right, right. That's something that I totally forgot about this C if framework language is that it's the compiler the standard is just a standard, right? Like there is
Mm-hmm.
no standard compiler. It's just a document
Right.
saying how things should be implemented, and then the compilers
Right.
do their
And
work.
in the early days of C++, there was what you might consider a reference compiler. It was called
Hmm.
CFront, and it
Oh,
was an extension of a C compiler with C++ features. So when people would speak about C++ and think of how that's going to affect implementations, they might look at an example implementation of the feature in CFront to see, well, what changes did that need over there? But now there's no such reference compiler anymore.
right. And then what made you migrate from C++ to the functional world?
So I stayed in compilers for quite a long time. It was about 25 years that I was working in and around compilers, either on linkers or front ends, to the point that I even started a company, well, joined a company as a partner with a friend of mine, David Abrahams. He did a lot of work with the Boost community. So I joined his company, Boost Pro, and we together did consulting work for compiler vendors. So if a vendor had a feature that they want added or changed in their C++ compiler, and it was something they didn't have an in-house team to do, or they didn't want to allocate their in-house team to do, we could come in as compiler experts and then just work on that front end. Usually it wasn't David and I specifically, we would hire subcontractors. So we had a whole group of subcontractors doing work for us. Some of those contracts were fairly involved. One of them took 2 years actually to complete and involved a whole lot of changes to the Clang compiler. And then I was doing that for a while and just realized, is this where I want to stay? Is this what I want to keep doing? And during that whole period of time, for many years up to that point, I love computing, but I had never found a computing language or a computing environment that was entirely satisfying. Emacs was the closest thing to bringing me pure joy when I would work with it, especially Emacs Lisp. But Emacs Lisp is not a general purpose language. You can't use it for all types of programs. So even though I would want to use Emacs Lisp for something like, say, shell scripting, it wasn't really appropriate for those problems. So I would look for different languages and try them out. And Dave would too. We would consult with each other and talk about what we had discovered in new languages. So he looked at D, for example, and I was doing a lot of things with Groovy or Ruby, Python, just always looking for that one language that I could really find as a home and do all of my thinking and experimenting in. And some friends of mine had been telling me about Haskell for maybe a few years up to this point. And every time they mentioned Haskell to me, I would look at it and the syntax just scared me the heck away. I thought, what in the world are they smoking that this looks like fun to them? And I tried to learn some Haskell at their instigation and failed at it multiple times. It wasn't until the third time of trying to learn Haskell from that online text, Learn You a Haskell for Great Good,
Hmm.
that something clicked and it sort of finally stuck. And that's when I discovered that all of that syntax I had thought so ugly, nearly every single one of those constructions was just from the library. These were just functions in infix form, right? They weren't actual syntactic features of the language, where I was used to C++ being filled with syntactic features. Whereas in Haskell, they're almost all library features. And that was really what appealed to me so much. And as I started getting into it, I discovered I have to get into this deeper. This has to be my day job for me to get to the level of expertise that I want to really be comfortable and familiar with it. So at a certain point, I told Dave, I think I'm going to leave this C++ compiler consulting work and I'm going to go work in Haskell. I'm going to just switch my career track. And I had a friend at the time from the C++ world, from the standards committee, also named Bartosz Maluski. And he was working for FP Complete at the time. And they were looking for Haskell people. But I told him, I don't know any Haskell, but I have this compiler background. So they hired me on that basis and allowed me to really learn Haskell and train up there at FP Complete. And I loved it. I just loved working in it. I can work in Haskell all day, every day, and it's very pleasing. And it's general purpose. I use it for everything now. Any hobby little utility I need, any piece of functionality I want on my computer, I just write it in Haskell now. It doesn't really even matter what it is.
So what was it that convinced you that this was the one language that really drew your
So,
attention? What's about Haskell?
so as I got into Haskell, of course, like any human created product, it has its own rough spots, right? Its own things that the community will itself tell you, hey, this isn't so great or this isn't so great. But just as learning Haskell caused the syntax to sort of disappear from my site because I saw how they were just library functions, Haskell itself I saw disappear when I discovered that it's just lambda calculus underneath, right? It's a variant of lambda calculus called System F. I believe it's System F omega, but it really is just this lambda calculus, which is where functional programming was birthed in the 1930s. And when I saw that it was just that pure, simple thing underneath, and every extension or feature of the Haskell language had an interpretation in the terms of that system, then really your mind just has to master that system and understand how these features translate down into it. And I suppose that even though you're never programming directly with the lambda calculus, it was the beauty of that I found so compelling. Because I can endure any ugliness in the language as long as I know that this is just surface. This is just syntax. This is something that maybe some future version of the language will fix. But nobody needs to fix lambda calculus. That has proven to be a satisfying expression of functional algorithms for many, many, many decades now. Of course, you extend it these days for different type features that you want. But if what you're doing is expressible as a function, lambda calculus is a very elegant form of expression, and it's that elegance that I find so appealing.
That is such an amazing answer, because first thing that I thought it would answer would be something like monads or purity or
Yeah, no, not at all.
because honestly, I think, well, when I think of Haskell, for example, I think monads is the first thing that comes to my mind, right? Because I think OCaml doesn't have monads, Lisp, like the other functional programming languages, monads just really shine in Haskell and make them work really well, and that really helps to maintain all the purity and allows you to write this beautiful code, right? Monads, I think it's an amazing feature.
Yeah, it is a very powerful feature. And whenever I'm writing a function and I realize, hey, my function takes in another function, and I have to call that function I'm being passed in various places, but I don't know the context in which the person wants to execute this algorithm. Maybe that function that they're handing me in should be updating state, or it should be printing to the terminal. But I don't care. I just want to give them the room to supply that context along with their function and have those changes to the context be threaded through the course of my function. Then I just lift my function up into the space of monads and allow that, the annotation of the return type to include that M. So,
Yep.
Whereas I was taking before something that returned an int, now it returns an M int. And all of a sudden, my library function, plays well with any monadic computation the user wants to do. I think that's a really beautiful way to give people the extensibility they need without having to build any extra features into the language for allowing that freedom of expression. So I will often write, when I write a library function, a foo version of it and a foo-m version of it that is just lifted up over the monad, so that you can inject whatever arbitrary stuff you want to go on while that library function runs.
Right. Modularity with functions, and like the functions being it's very easy. You come up with two functions that are doing widely different things, but if you squint your eyes, you'll see that all that's happening here is just mutating a monad in there. So it really helps with those. It's kind of these little building blocks, right?
Right.
That is
I'll
great.
tell you what I appreciate more than monads, though, in working with Haskell is I appreciate function composition
Right.
and I appreciate partial application. It really encourages me to break my code up into as many small functions as I might desire.
Yeah.
And each small function can be so targeted on just the one thing that it's trying to do. I can then focus on making as many pure functions as possible where I don't even have to deal with monads, not even in the generic form. And then I just mix and match and put them together like they were Lego pieces. And that makes for very composable and easily comprehended and tested functions. I have found sometimes when I'm working with Rust, which is a lot of what I do now in my day job, I'll be writing some code and I'll notice a pattern. And the pattern is very similar in two places, but not quite exactly the same. And my Haskell experience makes me want to lift that repetition out into a function. But that's not always so easily done because abstraction is not quite as natural in Rust as it is to writing non-abstract code. Whereas in Haskell, the difference between an abstract and non-abstract function is almost zero, right? You just use an abstract type instead of a concrete type, and that's it. Whereas with Rust, I might have to deal with lifetime concerns. I might have to deal with lifetime scoping of the type parameter. I have to use a different syntax to specify genericity. Then I might have to supply types at the call site so that it can infer the correct type. It can be done in Rust a lot of times, and I do look for opportunities to write helper functions to abstract patterns, but it just doesn't come as naturally. It doesn't flow as smoothly, and that means that I will sometimes defer that work until later, which means it may not happen.
So before we start talking more about Rust, which I definitely want to, you were saying that the one thing that really drew your attention is the simplicity where everything here is pure lambda calculus. It makes me wonder, is this because I know that you've done some work with Coq, you developed some libraries, and I think you're quite familiar with Coq. Is this time that you started looking at formal methods and actual programming languages research?
Yeah, that's exactly right. When I first saw the lambda calculus under Haskell, I started reading a lot of articles, a lot of academic articles about this side of Haskell, because this side of Haskell is referred to a lot in research. And as I went deeper and deeper in, that's when I started to discover that there were more flavors of lambda calculus than just the flavor that is used by Haskell. And that different typing disciplines put these lambda calculi on a cube. I'm sure you've read about the lambda cube. And dependent types really is one of the further out corners on that lambda cube. So it really made me realize that Coq and Haskell are related. They're definitely cousins. And they're unified at the lambda calculus level, but they have different typing disciplines on top of that underlying lambda calculus. I was also attracted to Coq because of how difficult it was. Haskell was very difficult for me to learn, and it took a long time for me to be familiar with it. And people kept saying, well, if you find that hard, this is even way harder. So I wanted to see, could I learn that? And I found that as I started learning it, it made Haskell clearer. It made Haskell easier to intuit and understand. In fact, now, sometimes writing type level tricks in Coq is way easier than in Haskell, because in Coq, you don't have to use special language or special extensions to do those things. You write them the same way you would write normal code because it's all just really one language, right?
Yep.
But in Haskell, if you want to have a value level function and you want to have a type level function, you may have to do different tricks with like closed type families or the way that you use type classes. There are ways to do it at the type level in Haskell, but you end up having to do them differently than you do for writing regular functions.
So how was your experience learning Coq? Was it as difficult as you thought?
It was difficult for a while, but I was assisted by two things. One is the amazing online learning materials, especially the one Software Foundations.
Oh, yeah.
So Software Foundations, when I did it, was one chapter really, and now there's 6 chapters. I can't recommend it to people enough. Even if you don't want to use Coq professionally, it's a great thing to do just to get insight into computer science and logic and how all of these data structures came to be and how they relate to algebra and a whole host of other topics. But I was working my way through the Software Foundations series when I was at FP Complete, but it takes a lot of time. I cannot tell you how many times I would finish work, then I would start working on Software Foundations, and then it would be dawn by the time I was done, right? And which would then impair my workday the next day because I would have to get up late. And it just became this vicious cycle. But I was so drawn in. It's one of the most fun games I have ever played is doing proofs in a proof assistant. So when I moved to my next job, which was at BAE Systems, where we did a lot of DARPA grant research, Coq was one of the tools they used to prove models and show correctness of the software that they were building. And BAE was really wonderful in giving me the opportunity to spend 9 entire months doing nothing but writing a register allocator in Coq. And that was where I learned the language enough to be fluent in it and use it for my own purposes comfortably and apply all the things that I had learned from Software Foundations. I'm not sure without that opportunity to have spent so much time just making mistake after mistake, constantly trying to prove false and days later realizing what I was doing. Without that freedom of time to make all of those mistakes, it would have been a lot harder for me to do all of that mid-career when that wasn't my area of expertise.
Did you have coworkers working in Coq as well? Because
I did. I had several who were familiar with Coq too.
right.
So I could bring up questions with them. I could show them code I was working on, problems I was having, and also the Coq community, the IRC channel. People there were incredibly helpful. Other people that I had met through BAE, actually, a friend you and I have in common, Ben. Ben Delaware. He also was a Coq expert that I could ask questions of during the time I was at BAE.
Yeah, that was one of the. I'm asking this question because that was one of my biggest issues learning Coq in Brazil. I was just so drawn in. It was really hard for me to get the feedback I needed because there was not many people working on it over there.
Right.
That's what made
Right.
me come here. That's why I was wondering. You sounded like you had such a good experience. And I'm like, he must have had people working with him.
Yes, I did have a couple. I think I had two people working with me who had a lot more Coq experience than I did. And then friends within the Haskell community who were sort of bilingual and they could do either Haskell or Coq.
In your experience, how do you think it is to learn Coq, given that you already know Haskell?
Well, let me say that learning Haskell was so difficult first because I came at it from the mindset of a C programmer. So in C, a variable is the name for a slot in memory that you can mutate. That is such a foreign concept when you're thinking in terms of Haskell, because in Haskell, a variable is the name of a value. And whether that value is actually represented as a cell in memory or not, that's totally up to the compiler. It may decide that what it knows about that value can be just streamlined into the code itself, and it may disappear and never exist as a memory cell. But it's hard when you see the word variable on the C side, also called variable on the right side, and not realize that one has the computer programming meaning of variable and the other has the mathematical meaning of variable. So there were a lot of things I was used to thinking about and ways of approaching understanding code that just made Haskell incredibly hard. My mindset was totally operational. It was totally about how data is represented in memory. It was wanting to read code by running a compiler in my head in order to understand how it would do what it was going to do. Whereas in Haskell, it's more about what the result of the function means, and the sequence does not necessarily, unless the sequence has a semantic impact on the return value, you don't necessarily know in which order things will happen. That's not meaningful. Unless, as I said, like monads are involved, in which case sequence might actually impact the answer. So if you know Haskell kind of in the right mathematical way, where you're not thinking of it in with the mindset of an imperative programmer, then Coq isn't so terrible. It is hard because dependent types are a little bit hard to get your mind around. But the Software Foundations course that I was mentioning earlier does a beautiful job of revealing these concepts to you one by one, step by step. It does not start you out with dependent types for quite a few chapters, actually, until it finally presents them. It starts you out with, well, what are types, right? Types are kind of just like mathematical sets that have membership or they don't, or the thing is not a member. And so values are just members of these specially named sets. And the type allows you to describe what the possible membership of that set will be. Very mathematical understanding of types. Whereas on the C side, I thought of types as prescriptions for bit patterns and how bytes should be laid out in memory. So I love the fact that Software Foundations does that. And I needed that to really kind of understand comp sci finally. And as I was learning these things, these foundational things, then it would alter my interpretation of what I read in Haskell. And then Haskell got easier as a result. So I can't even say really that Coq is so hard, more that Coq was hard for a mind like mine that had been trained in that way. Coq, as I said, because the term language and the type language are unified, in a lot of ways, there's a beautiful simplicity to it. The way that you think is, what you learn as in terms of how to write functions, you can lift all of that over to how you write types. And then you could write fantastically complex types, but you're relying upon everything you know how to do with functions. And so that, in that sense, is much easier than it is in Haskell. Where Coq gets hard and where it starts to break your brain a little bit is when you do dependently typed programming. So using dependent types to specify complex types, like in the formulation of theorems, is awesome. I mean, that's really where Coq, I think, shines, is using dependent types to state theorems. And theorems, by the way, are just types. There's a thing called the Curry-Howard correspondence that says theorems are types and proofs are programs. So when you use dependent types in Coq, you're usually using them to express a type that is very rich in what it conveys. It's saying that, for example, this function I'm calling sort, there's this theorem that I have said about sort, which says the value that comes back from sort is a list of the same length whose elements are ordered and where it is a permutation. So those three, I guess permutation includes the length constraint. But expressing that as a type requires dependence, right? Because the type of that theorem depends upon the value that comes out of sort. And that is a way of using dependent types that is very easy to do and it's very natural. I mean, you already kind of do it. If you write math theorems today down on paper, you're already using dependent types because you're saying for all x, and then you're involving x in some type stated theorem. Where Coq gets harder is when you have a data structure that uses type dependency, and then you use that data structure to write a normal function. So you want the return value of that normal function to be a dependently typed value, or an input parameter to be a dependently typed value. Now Coq has to figure out, well, how do I compute whether the thing you're returning is really an inhabitant of this type? Well, the type is not a mere set anymore that it can check for membership. The type is itself a thing that is being constructed by the result that you're returning. So the result that you make might change the type of the answer. For example, you might write a function that takes a variable x, let's say it's an integer, and the result of your function says, well, if x is less than 10, my return type is a Boolean. But if x is greater than 10, my result type is a natural number. Now, which set your value has to be checked against depends upon the value of that number coming in. So Coq has to figure that out. Coq has to understand what the value in that number is, and then how that's going to yield one of those two different types. And you assist it in discovering how it's an inhabitant of that type using the proof environment. And you interactively, you do things like, I'm going to induct on the number now, and I can destruct on a test of whether the number is less than 10 or not. And if it's less than 10, I know that I'm dealing with a Boolean. And if it's greater than 10, I know that I'm dealing with a natural number. But it quickly can become very complicated. The classic example of taking two vectors in of lengths m and n and returning a vector that is, say, of length m plus n is very hard to write in Coq, because now the vector has all of its own inhabitants and the type indices are themselves natural numbers. So you're now inducting not only on the vector that you received in as the argument, you may be inducting on the type index of the vector that you received in as the argument. There are other dependently typed languages like Agda that make this easier to do. So Agda makes writing dependently typed programs easier to do. It doesn't give you the nice interactive proof environment for working with dependently typed, let me call them theorems for the sake of distinguishing them. Whereas Coq gives you a wonderful interactive environment for proving theorems, but its facilities for writing dependently typed programs can sometimes just make you have to scratch your head. There are some constructs you have to write, like I believe it's called the cargo pattern, or is it the convoy pattern? I always forget which of those two it is.
You're probably talking about the convoy.
Yeah, convoy pattern. Yeah. So the convoy pattern is a very well-known thing that you have to do in Coq that Agda kind of makes automatic. You don't have to do what the convoy pattern is. But in Coq, you have to do it. So you're, in a way, manually destructing on a dependent value and then presenting the rest of your code with what that implies about the type indices of that value. So if I destruct a vector and I get a certain term of that vector type, well, then it tells me, it implies something that I now should know about the type, the numeric index of that vector. But Coq doesn't automatically give you that evidence. The convoy pattern is a way to capture that evidence and make it available to the rest of your program, whereas a language like Agda will give you that evidence. There are libraries, however, that have come out for Coq that make this easier to do. So if you're a newcomer to Coq, there's a library I really recommend to you called Equations. And like Michael Klein that I mentioned at Tezos, he uses equations quite heavily. And I use equations now everywhere as well. And what equations will do, one of the things it will do is when you destruct on a dependently typed value, it will take those implied results of what it tells you about the type indices and present them to the function that you're writing so that you can use them as witnesses in constructing your proof. Equations, though, is not as naturally built into the language as this facility is with Agda, but it does provide enormous convenience. So now you can write a vector library that works with length indexed vectors, and the code that you write looks a lot like what you'd write in Haskell, but it's handling all this dependent typed stuff. Whereas a plain vanilla Coq implementation of a vector library is going to involve a lot more code than the equivalent Haskell would have, just because you have to use the convoy pattern in a lot of places and deal with these type indices and how they get destructed.
Do you think that learning Coq made you a better programmer?
Did it make me a better programmer? I think it would definitely made me a better thinker about program design. Like when I do architecture reviews at Dfinity now, the main thing that I ask myself, which yields insights that are sometimes useful in that architecture review, is how would I do this if I wanted proof to be easy? Like, how is this making proof hard? The choices being made. And that one thing alone very strongly affects how I review things. And so I may like one person presented a data structure where it was a data structure along with three things that you could do that it represented. It either represented an insert, an update, or a delete. And I thought, well, now to prove, I have to prove things about this data type. I have to consider these three cases. I thought, well, what if the data were separate and the insert, update, delete were just a policy, and it was an extensible policy format? Now I can prove things about just the regular data in itself and then have like extended proofs for each of the different policy cases. And the people I was reviewing with said, oh yeah, that actually would be a simpler design. It was a little too late in the review process to rewrite all the code in terms of that design. And I drafted out in Haskell a prototype of how that design would make the code we were working on simpler. But that would have never occurred to me, I think, without the Coq experience of seeing that some code choices make modeling or understanding the underlying semantics of your program, they just naturally obscure it. They make it harder to understand what is the meaning of what you're writing.
Yeah.
And one of my good friends, Connell Elliott, he's always asking the question, well, what does it mean, what you're doing? Don't ask, how do I get the computer to manifest the behavior I want it to manifest? You ask, the thing I'm trying to do, what does it actually mean? And if you just keep hounding yourself with that question and going deeper and deeper and deeper, you'll realize that many of the choices that we make in the architecture process, they're incidental. They are choices of optimization. They're choices of representation. They're choices that are basically forced upon you because of the environment in which you're realizing your solution, but they have nothing to do with the fundamental underlying construct that you're trying to express. And what Connell has done in his work, and which I find very beautiful, is he has found that if you go deep enough, most of the things that you think you're inventing are just recastings of mathematical ideas that seem novel because of the environment in which you're trying to realize it. But if you could see that underlying mathematical object independent of that environment, it would give you so much more insight into whether you're making the right choice, what other implications your choice might have, whether your choice would be amenable to parallelization. You might not have thought about that initially because we're used to thinking sequentially with the types of machines that we use today. So it's that burning away of the exigencies of the now to see if we can find that little kernel of truth related to the eternal that lies at its heart. And I think languages like Coq, they can get you more into that mindset because they allow you to not only write programs that compute values, they also let you express relations that are mathematical, that may not even have a computational representation at all, ever. Like a mathematical set, some people might represent it as a list, but truly a set does not necessarily need a computational representation. And if you're going to lift into the realm of infinite sets, well, then you can't have computational representations anymore. And what Connell has expressed to me is that a lot of interesting human ideas are in the realm of the non-computational, but they have expressions or approximations in the computational domain that are valuable. It's only in a language like Coq or Agda or Idris or something that gives you dependent types and that has a non-computational domain like prop or set that allows you to even write code that's over in that other side. Otherwise, that's mostly the domain of mathematicians because they're the ones who are used to having tools that may not have computable representations. But programmers, like everyday programmers just using Rust or C or C++, even Haskell, they're always in a computable domain. They're always working with a concrete representation. And it just makes the mind reach for implementation as the first expression of whether an idea is feasible and makes sense.
Wow. That was really deep. Those things that you were talking about, dividing the policies, I can see a direct representation of that, of how you would do that in Coq, because that's a continuous concern that you have in a dependent type language, is that how do I reduce the use of dependent types the most as possible in the data level? Because when you're programming over those, that's a huge pain. That's a huge pain because then you have to prove things while you're programming, and you don't want that. So right. I can definitely see it, how you're trying to get that out of your data and then try to somehow model it somewhere else, right?
Right. I have a great example of what you're talking about in my register allocation library, because you have these basic blocks, right? And every block is going to have a bunch of slots in it for variables where you need to allocate those variables to registers. So my blocks were naturally dependently typed because I wanted to have all these properties hold for every block that ever existed anywhere, rather than having a basic block and a separate structure that said whether that block was valid.
Yeah.
So I have this dependently typed block, not realizing my mistake, and I wanted to fold over a list while constructing a block as a result of the fold. Well, that meant that not only was the block changing at every iteration of the fold, the type indices on the block were changing at every iteration of the fold. So I then had to write a dependently typed fold that allowed you to change the indices at every iteration.
Oh my God. And then your accumulator have to accumulate the proofs somehow. And
Yes, exactly. And then the proofs over code that used the dependently typed fold had to take all of that into consideration, because you can't easily rewrite deeply into code that is usually at higher level, right? If you have a function that takes a lambda and that lambda is changing a type, it's really hard to rewrite types underneath that lambda. So this ended up being like a bomb that destroyed whole months of my productivity. And I didn't realize that it was all because I'd done what you just said. I had failed to sift out the proofy bits and have them occur after the fold, and then have just one proof that shows that the fold always preserves the proofy bits. Instead, I tried to tie that obligation to the data, which now gave my data no intermediate realm in which it could be maybe for at least a short period of time invalid, as long as the result was valid. Because that's usually what we care about. We care about that the final product is perfect. But if the transitory states in between are imperfect, that's okay if the environment can prove that the end result is always perfect.
And that
There
is
are
not
these
gonna
functions.
that's not
Go
gonna
ahead.
get out of there imperfectly, right? Like that there is no
Right.
access out of this realm being imperfect. Yeah.
Right. So like even in Haskell, there are functions like head, taking the head of a list, and we call those functions partial because they only work on certain types of lists that have more than 0 elements. So people say, well, maybe we should get rid of head, or maybe we should require head to, uh, always return a maybe value to take into account the case where it's 0. But if you think about it, there are certain functions that if you compose them with head is always okay, because the function you're composing with never returns an empty list. So in those circumstances, head might be maybe a little bit fishy, but the composition is never fishy. And so in Coq, you want to be able to say things like that, where I'm going to give you building blocks. And each building block may not be the be all end all and give you the correctness you want. But if I have a proof that shows that certain compositions are the correctness that you want, then all you need to show me is that you used one of those compositions in building your program. And then I know that your final answer is good. So yeah, Coq does also teach you about this kind of thinking, that there are ways of approaching the problem of correctness and verifying software, that you don't just want 100% correctness all the time everywhere. You want correctness where it matters so that you can show that you always give the right answer.
It is amazing to me how this notion of compositionality somehow is so central in computer science. Everything we do, everything we care about, this always comes back. Modularity is a way of thinking of proper compositionality. Even monads is a way of thinking of proper compositionality. The O operation for functions in Haskell, it's all about compositionality again and again and again. And this really makes me think of how interesting category theory is for us in computer science, right? Because
Mm-hmm.
that's pretty much all we're doing in category theory
Yeah.
is composing things together.
Yeah, it's a theory of composition, really.
Yeah, it's
and
very
yet at the same time, how odd it is that the most popular imperative languages like C and Rust and Java and all of these, they're not founded on compositionality. And I think that they realize that that piece is missing because they really stress modularity,
yeah.
right? They have reached for APIs and interfaces as a way to try and recover some of what you get from compositionality, the ability to create small pieces and put them together.
What was the project you were working on BAE? Can you tell us more about it?
There were several contracts that we worked on for DARPA there. I was hired to work on a project called Crash, which was building a custom compilation pipeline for a chip that they were designing from scratch. That was the project we were applying Coq to. And then after that, we did a project called Brass, which was high assurance software. So basically, you specify what your program is going to do at a very high mathematical level. And then we were working on creating an automated pipeline using MIT's Fiat library to produce an end result that could run on, military hardware that would stay within the bounds of that specification. And that was all in Coq. So during that 4 years, I was working in really nothing else. Whereas on Crash, I was working in both Haskell and Coq. And then by the time the Brass project ended, some of the people who had been working at BAE because of Brass, because of Crash, they were leaving. And when the other coworkers of mine who knew Coq also left, then I left as well, because it's hard to bid a contract for a language that you only have one expert in.
Yeah,
It makes it very hard.
especially Coq, where doing proofs it just takes such a long time, and
Right.
It's very complicated. What sort of properties were you guys interested in improving?
That's a good question. I'm trying to remember in Brass what the candidate software we were looking at was. I know we had different sample problems because on a DARPA contract, you're not building a complete system. You're showing viability for an approach. So really, if you can show that programs like this can be written and succeed, then the end result of your project, if it is turned into a real functional product, they don't always, it will, of course, usually be applied to a totally different problem. So you're proving feasibility and viability. So we had simple things like the hotel problem, where you have a key card assigned by a hotel, and then you want to make sure that if somebody turns in the key card, that it can't be used to unlock the door before the next guest gets their card. That was a project we did in ACL2, actually, not in Coq. The Coq one, it's really kind of skipping my mind right now because this was about 2-3 years ago that I was working on this.
That's fine, don't worry. So you also worked with ACL2?
Yes,
How do
we used ACL2 on a separate. It was a third contract.
how do you compare Coq and ACL2?
Well, ACL2 is interesting. If you were to use Coq in a way that auto was the only keyword you allowed yourself, you'd basically be doing a lot of what ACL2 does.
Oh, but
Because in ACL2,
auto is
go
not
ahead.
that powerful though.
It's not that powerful, but if you see Adam Chapala's crush tactic, I mean, there's ACL2, right? Except Coq has higher order functions, and Coq has basically non-computable domains as well, which in ACL2, you're in a Lisp variant that is untyped, and you're often dealing with executable functions, things that can evaluate to a result. So ACL2 will do a proof search and a rewriting scheme, and it will use induction also the same way that Coq does. And it will search through this database of all the theorems you've proven up till this point to try and find out if it can find a way to the proof term that you're looking for, and it will use Z3 to assist it in that search. So if you set it up well, it's a very effective system because it doesn't require you to do any proof engineering. You just have to set up the theorems in the correct order and with the correct structure for ACL2 to be able to make good use of them. And you can add hints and you can say, like, I want you to induct on this pattern, or I want you to apply this theorem if you see these things in the goal. And Coq is a little bit more on the manual side.
Right.
You can set up similar automation machinery, but it takes a lot of work, and keeping that up to date. I mean, you've done this before too. Keeping it up to date as the code evolves can be rather challenging. Recently I've had an opportunity to compare and contrast the two because one of my recent personal projects in Coq has been a formalization of an LTL axiomatic basis that was developed by Professor Warford and Scott Staley, his research assistant. We've been working together on a formula. Well, they had been working for a long time on a formalization of ATL on LTL on an axiomatic basis. And they used ACL2 and a semantic model implemented in ACL2 over streams of Booleans to show that all of the theorems that they had developed on top of this basis were correct. And then my contribution was to do all of this same work, but do it in Coq, so that all of my proofs of their theorems were use only the axiomatic basis. They don't use a semantic model. The semantic model is a later instantiation of that axiomatic basis that I then use to show the soundness of that choice of axioms. And by doing this, I was able to show that their set of axioms could be reduced by three axioms. And we found some interesting and novel axioms that we haven't been able to find in the literature yet that allow many of these theorems to be proven. And what's interesting is that we keep the two systems side by side and we use them both. It's easier for us to check whether a theorem even makes sense by asking ACL2, can you find a solution to this theorem in your semantic model? And if it can, then I know that I'm not trying to prove false when I go to do it on the Coq side, where it could take a lot more work because I have not built up a huge library for automating these proofs, since a lot of it deals with these rewrites of these axioms. So that's been an interesting endeavor to see Coq and ACL2 side by side, and how they have experience with the ACL2 development. I'm bringing in the Coq experience with my development, and we sort of go back and forth and use the two at the same time.
That is so cool. Does ACL2 have dependent types?
ACL2 does not have dependent types. No, it has no typing at all. You
Really?
simply describe your inputs with Boolean functions. So if you have a function that works over a list of Booleans, you say for all X, and then you say where X is a list and where every element of X is bool P. So in a way that's typing, but it's typing by inspection of the value rather than having a type
Right,
language.
right. Yeah, that's very different. Very different. Wow, those are really cool jobs. Do you do any sort of formal verification nowadays at Affinity?
I starting in October, I switched to the research side of Dfinity. I was previously in the engineering side. Now I'm in research, and I'm specifically working on a lot of the financial aspects of what we do there. So we have the blockchain that runs all of the contracts. Then we have some system contracts that are special to the system. They were present at Genesis, and they run in their own secure subnetwork by themselves. And so one of them is the ledger that tracks token balances, and the other we call governance, and this controls how people can stake their ICP in order to gain voting power and then vote on proposals, receive rewards for those votes, retrieve the income from their staked tokens from all of that voting activity. So this is governance in the ledger. And I've been doing a lot of thinking about how do we show correctness of these smart contracts. So I started a Coq model of the governance, and then have used Haskell also for modeling some behaviors of the network, and really just sort of now getting into this. And we have a team at Dfinity focusing on formal methods, and I'm hoping that we get to do more Coq work together. Although for the time being, I'm the only Coq engineer on that team, and more has happened in TLA plus than has happened in Coq.
How do you guys work? What are you doing with TLI Plus there?
Just so when the ledger and the governance canister, they can run asynchronously, yet they talk to each other. So TLA
Mhm.
plus is being used to model the interactions between those two to make sure that there are no sequences where there could be deadlock or there could be race conditions. Whereas the Coq model I did of governance is only of the algorithms it's running and none of the operational aspects, such as the asynchronous execution.
TLA Plus is a lot simpler than Coq and ACL2, right?
Oh yeah, definitely. It's effectively, it gives you a way to build up a state machine and then provide assertions on the global state and on local state, and then it will run with Z3 through all the possible different threadings of operation through your different processes, and will tell you whether it was able to find a sequence of events that could lead to a violation of either global or local state. Properties.
Yeah, I can see how you can do a lot with that, but for example, you don't get induction, right?
You don't get things like induction, no. Yeah, it's a different beast, right? I think
Hmm.
I think it's an incredibly valuable tool as well
Yeah.
because it's much easier to use.
Oh yeah.
They offer so there's a surface language on top of TLA plus called PlusCal, and PlusCal lets you write in a very C-like dialect where you write functions. So a function, you call it a process as a thing that can run asynchronously, and then you have your inputs that you specify as arguments, and then you just say things about your arguments, like I always want this to be a list of even numbers, or I always want this list to be less than 100, or all these other things. And then other processes that are calling that process, it'll have that assertion be validated every single time. But you're not asserting over values per se, you're asserting over these models where Z3 is now crunching through to find, is there any sequence of values that I could be passing around that would trigger an execution flow that would cause a violation of one of these things. And so in relatively short order, you can get some effective results. I will say, though, that it becomes computationally expensive very fast, much
Wow.
faster than, say, ACL2. I've seen ACL2 proofs that took 24 hours, but I know that there are TLA proofs that take 7 days, even at
Wow.
Dfinity.
Wow.
And that's 7 days on a 64 core machine using many gigabytes of memory, because as you write more and more complex models in TLA plus, the state space that Z3 has to explore gets huge fast, and it can easily become exponential. So then there's a separate kind of expertise you need when working with those models, which is simply state space pruning.
Hmm.
How do I write my property in a way that gives me meaningful and effective results, but causes the least number of possibilities to be explored? So you're always looking for opportunities to short circuit and say, well, if these two things happen, then I'm sure, for whatever reason, I'm sure that things aren't going to go south. So don't even search that space, because it's always going to be positive.
Wow, that's a very different set of skills than say Coq, for example.
I think
that is
so.
very
I think
interesting.
so.
It's very interesting. So you said that you are working on Coq, and then there are other people focusing on TLA plus.
We have a few different people. I mean, one person works in TLA plus, another person has used Tamarin for doing security proofs. I've used
Tamarind?
Coq. It's called Tamarin.
I never heard of that. What is that?
I have not done any research on it, so I really don't know how to tell you. I have the paper that my colleague produced from the results of her Tamarin proof, but I believe it's used more in the security protocols community.
Oh, okay.
Tamarin. Another coworker was very, very strong in Agda and had used Agda to prove properties of another blockchain. So when he came on, he brought some of that, and we were looking at different ways we could use that. I guess we're still open, because now the formal methods group only really just started a couple months ago.
Mm-hmm.
And we're still looking at what tools do we want to employ, where do we want to employ them, what do users think is going to have the best benefit. Another thing I would like to see happen is not just verification of the software that runs the blockchain itself, but also a toolkit that users can use to verify their own smart contracts. So if you're a user and you want to write a DeFi contract and you want to ensure that there's no way that people can hack out money from, say, a distributed exchange that you're building, I want you to be able to write your code in such a way that I can provide you some evidence that it's going to have the properties you expect.
So I was actually I was doing an internship at Nomadic Labs. They work for Tezos, and they're thinking exactly about the same problem you're describing.
Yes.
Maybe I should put you guys in contact, because I think you have a lot in common, like of sort of set of problems that you guys are putting your hairs out, right?
Oh, definitely. I mean, I would even say for a future episode, contact Michael Klein. He worked as a Coq engineer for Tezos on their proof architecture for canister building.
Oh yeah, for sure.
He and I have talked quite a number of times, a few times already, and I'm fascinated by the work that he's been able to accomplish there. He's the first person I've seen in the blockchain space actually use the homotopy type theory variant of Coq to do proofs, to do real proof work.
Wow.
Very impressive.
That's going very deep then.
Yes.
Now, earlier you have mentioned that Dfinity started doing work with Haskell and then migrated to Rust. What happened?
That's right. What happened?
Yeah.
So Dfinity, actually, believe it or not, the very, very first version of our blockchain ever was written in JavaScript. Even before Haskell.
Wow.
Yeah, that was the proof of concept.
Why someone?
Well, I mean, it was really to get the network running as quickly as possible, and it allowed investors. It gave them enough of a functional blockchain that investors could purchase tokens during those early days. And then that experience was moved into Haskell. We had a few Haskell engineers at the company. When I hired on, I think there were maybe 6 of us Haskellers. And we worked on building the network. But as the network was moving and progressing, and we were trying to bring it towards going live, we realized that there are a lot of operational concerns that you have to think about and deal with that Haskell does not give you a super clear way to express or reason about. So Haskell is amazing if what you care about is the result. Like if I were to write a compiler, I would definitely want to write it in Haskell, because I would want to know that the executable code I produce is a proper result of my compilation. I might even want to do it in a dependently typed language to have an even stronger guarantee, but Haskell tends to be so easy to write stuff in. But if you need to determine exactly how that compiler is going to run when it produces that executable, how many bytes of memory is it going to use? How fast is it going to go? How does it scale with the size of the input text? To really build that knowledge into your Haskell program, which can be done, by the way, takes a different set of skills. That's a level of expertise with Haskell, this operational side of Haskell, that requires a deep understanding of the runtime, of the garbage collector, of how the heap is laid out. And we had some of that expertise. Like we had Joachim Breitner working with us, and there's really no one I know better at understanding heap and how to make programs memory efficient. But it's hard to hire that, right? A lot of the people we were interviewing from the Haskell community were on the more academically inclined side, because that's why Haskell draws people in, how beautiful a language it is, how well it expresses functional programming. It's not pulling in C engineers, right, who want to use a different syntax to do what C does. So as we were finding this difficulty, not just getting people with this black hat or this black magic understanding of operational Haskell, but who also had production experience building such systems, shipping them, and keeping them operating for at least a year. That became such a narrow field of people that we wondered, is this the right language for what we want to do? Are we painting ourselves into a corner by creating this dependence on such a small hiring pool? If I could have found the people, I think the argument could have been made to keep Haskell. But instead, we decided to switch to Rust, because if you know C++, you can learn Rust very easily. And a lot of people in the C++ world do have this experience. They're used to building systems that have to run to particular specs and to keep them running. And Rust just gives you a nicer language to do that, because you get more guarantees on how memory is going to be used and how threads are going to interact. And so once we switched to Rust and started rewriting the whole project, it was much, much easier to find people.
Oh, wow. How long did it take to rewrite the whole project?
From the day that the rewrite started until launch was a year and a half, about.
Okay. Wow.
Yeah.
You really wanted to change.
Yeah. And when you consider the complexity of the system that we have running, getting all of that working in a year and a half is remarkable. So a lot of what we learned from the Haskell implementation helped inform the Rust implementation. So it really did help us get a leg up on what we wanted to write.
Nice. And how do you compare the two implementations? Are they similar in modularity and features and easy to maintain and use? How do you compare them?
Well, it's hard to compare them because the Haskell version never shipped. So there were a lot of things that are now very important considerations in the network that the Haskell version didn't have to deal with. What I do appreciate more about the Rust version is that it is much easier to do code reviews. In Haskell, because of the way type class lookup works, because of the way it's so natural to use higher order functions and to stuff functions into data, sometimes you weren't always quite sure reading a code review what that code was actually going to do at runtime. Rust is a lot more like C or C++ in that regard, in that what you see the code proposing to do is probably what the code is going to do. Of course, there are traits. There is possibility for indirection, but you just don't end up leaning on them as heavily. Like all of the traits that we use are only there so that we can have a production version and a testing version of different components. But in production, there will only ever be one instance of that trait.
That really sounds like a main difference between a functional programming language and an imperative language, right? Because in a functional programming language, we're talking about a declarative style where you, in a sense, tell here is what this code is supposed to do by the type system, right? And an imperative, you're giving the step by step of what's going on. Plus, in Haskell, I can also see how the type classes does a lot of magic under the hood for you, right? Like with the searches and everything, inferences. Yeah.
I do often recommend to people who are starting out in Haskell, and I do this myself now as well, write the simplest Haskell you can get away with. I
Hmm.
consider it a triumph if I can write a function using only basic types and functions and almost no features. The features that I do like are the ones that are purely for syntactic convenience, like view patterns or record wildcards. But if I find myself using undecidable instances, it's usually because I'm required to do so because of a library that I've chosen to use. I recently started using open unions in one of my personal projects, which is basically like an n-ary either type, right?
Hmm.
And that required me to use undecidable instances for the way that it finds which alternative is the inhabitant of the type. And that's okay. I mean, if it's the library needing me to do it, then that's okay. But if I'm writing code that needs me to turn on undecidable instances, then I wonder, what am I doing? Am I buying really anything from all of this uh, wizardry, or could I have done it much simpler by just using plain functions?
Yeah, my old advisor, he used to say that language as extension in Haskell is slowly killing the language because they're too powerful, right?
Hmm.
They 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 change the language deeply in ways that they're not necessarily the best. And what are your do you have any thoughts on language extensions?
I wouldn't say it kills the language because they're all optional.
Yeah.
You don't have to turn them on.
Well, I think his main point is that when you're reading a paper, for example, often enough they would use some language extension and would not be explicit about it, right? And you get lost and
Mm,
like, I don't know what's going on here because basically he's using a language that didn't properly define what is the language that he's using, right?
right. That's true. That's true. And when I do come across a colleague's work in Haskell where they've turned on a zillion extensions and they're using them to the max, then I do find that it's not it's not really the most maintainable. I remember a question that was asked of me by my manager at the time at Definity. Wonderful manager, Mac McCauley. And he was the one who was asking me, should we rewrite all of this in Rust? And I remember one evening we were there talking and he said, I want to know why we should keep Haskell. Can you tell me why we should keep Haskell? And I said, yes, I'll write up an article, right? I'll convince you that we should keep Haskell. And he said, okay. And he's a very open guy, totally willing to consider that. He said, let me just put one constraint on you. As you write this, keep this in mind. If you say that we should use Haskell, I'll let you use Haskell. And we'll hire the people, we'll find the resources, we'll do it. The only constraint is you don't get to write any of the Haskell. He said, do you still want to do it then? Meaning that I would simply be overseeing, right? I would
Right.
be code reviewing, I would be design reviewing, I would be doing all the team lead type stuff, but the actual coding and choice of feature extensions and all the rest would be done by everybody, and whatever standards we chose to come up with. And when he said that, it really changed my thinking, because why I love Haskell is because I get to use Haskell, right? I want to have a day job where I'm writing Haskell all day. Do I want to have a day job where I'm reviewing Haskell all day or trying to get different engineers to use Haskell in the same way? And then it suddenly dawned on me that that can be a daunting task,
Right.
depending on who you're working
Yeah.
with, what their personalities are, what their preferences are. Rust is, in a way, a little bit Procrustean, right? It cuts
Right.
off your legs if they're too
Yes.
long, or it stretches you out.
Yeah.
It fits you into a pattern of use.
Yeah.
But if you have to work with 100 people on a complex project across 2 continents, because we're some of us in the US, some of us in Europe, that becomes a feature. That becomes a very strong feature.
Huh.
So I won't say that personally I'm overjoyed that I don't get to use Haskell as much anymore. But when I write code in Rust now and I have to share that code with colleagues and hand it off to them and have other people maintain it, I do appreciate a lot of those features.
Yeah, I started using some Haskell for the first time this semester because I was a TA for Ben's class, so he was teaching PL for undergrads. And at first I was really excited because Rust is this new language and everyone's talking about it, right? But then when I got hit for the first few errors of like lifetimes and boundaries and like I didn't even understand what's going on. I'm like, just let me run my code. Come on. This is not. It was not. It was not anything too. too big. It was like a little interpreter for a little language, and I couldn't get the pointers to just run.
Mm-hmm, mm-hmm. Yeah,
But
sometimes I wish for a no lifetimes flag that'll just let me segfault. At least then I'll get to see if I'm headed in the right direction.
yeah, exactly. But I think you get used to it, right? That's my hope.
You do, you definitely get used to it. I still find to this day that putting lambdas inside of data structures is a recipe for pain.
Hmm.
So I avoid that now wherever possible. That one never gets all that easy, right? Because the lifetime of the values, the variables being captured, is different. Has to sync up with the lifetime of the closure itself. And so then when you want to put that into a data structure, then that has to propagate out to the lifetime of the data structure. And it's now several different lifetime arenas, I guess you would say,
Yeah.
that, or regimens that you have to now think about. The data type, the closure, and what you've closed over all have scope that is rather dynamic.
Yeah. That's a good way to put it. Well, now while we talked about your huge work experience, you worked on C++, a lot of C++, a lot of Haskell, some Coq, or a lot of Coq maybe,
Mm-hmm.
and Rust. Now, while all of this was going on, you also had quite some contribution on Emacs. Do you
Right.
wanna? What do you have to say about that? How was that?
Well, I found the Emacs editor when I was a teenager, actually, and then I used it heavily, but didn't really extend it at all. And then I saw somebody use VI the way VI was meant to be used. I mean, he would sit there and he'd maybe press four keys and entire reams of text would appear on his screen. I was awed by it, and I had to learn, what is he doing? So I read every book on VI I could possibly get, cover to cover, and I wanted to master this editor the way that he had done. And I loved VI. I still use VI to this day whenever I'm in the terminal or whenever I'm connected to a machine over SSH. But a coworker way back introduced me to this VI emulation mode for Emacs, and it was very accurate at the time. And the maintainer of that package actually accepted my suggestions when I would find differences from the behavior of real VI, and he fixed this emulator in Emacs. And so he created an environment where I had exactly the VI I was used to, but now I had multiple buffers, and I had a directory editor, and I could show all my buffers in another buffer as like a menu and interact with them. And all of a sudden I started to realize that VI was a great editing paradigm, but Emacs was a great environment. And about this time, this same coworker introduced me to the Lisp subsystem of Emacs and how I could use that Lisp system to extend the functionality of Emacs and configure it. And so I printed out the whole manual for Emacs Lisp, had it on my desk. It was something like 700 pages. And whenever I was waiting on compilation, which we had a system that compiled really slowly, I would read page by page and just keep tossing the pages that I had read into the recycle bin. And in that way, over several months, I read the whole Emacs Lisp manual, and I was writing now little features. Like there's a feature in Emacs right now where if you do meta x align, it will make things line up into a column. So that was the first contribution I ever created for Emacs back in it's like 1994 or 1993, I think. And it was a whole lot of fun to write. And it sort of turned me on to this idea of an extensible environment that I could craft to exactly what I wanted Emacs to be. And over time, I started to realize that Emacs also had a philosophy. It had a way of looking at the structures and the hierarchies of all of the things that it does. For example, P is a letter related to things being previous. So you have control P to go to the previous character, the previous line. You have meta P to go to the previous I forget what meta P, is usually configurable, but it's usually previous something according to the mode. You have command control P to go back to I think it's the previous page, but like this P-ness infects all these different key bindings so that they all deal with previousness in some way. And the same with N for next. And there's a lot of there are a lot of characters that kind of represent families of conceptually similar things. But of course, VI breaks all of that because VI has its totally own way of thinking about movement and which key bindings relate to movement. So I found ultimately that if I wanted to get the true value out of Emacs, I had to leave the VI editing experience behind and just take the time and learn the Emacs editing experience. And I still find to this day that if you're just manipulating text in a buffer, VI is quicker because you can more efficiently tell it exactly where you want to go and what you want to do. Whereas if I'm creating text, especially if it's structured text and I'm in a mode that's built for that thing that I'm creating, like say Rust, then Emacs is way better because it gives me a lot more facilities for bringing matching things into being at the same time, a template expansion, et cetera, et cetera. Of course, all of this is in reference to VI, not Vim. Vim has become its own thing and is very modern. It has a lot of these same features also. But this was sort of my journey. And as I got deeper into Emacs, then of course, I started creating and writing more and more customizations and modes and things like that. And always sometimes it was an idea that I would have like, oh, wouldn't it be cool if Emacs did this? But the majority of the time it was just, oh, I need something that does this. Like the thing that I wrote that is used the most by other people now is called usePackage. And usePackage was never designed as a good idea. UsePackage was solely designed as, how do I keep myself from repeating myself in my init file? Because I noticed that there were certain patterns to every single package I wanted to configure. And every time I would learn a new trick or find a more efficient way of loading my init.el file, I would then have to retroactively fix that same pattern throughout all of these customizations. And in my current Emacs configuration, I have over 400 different external packages being pulled in and configured. So that was untenable at the manual level. So all that usePackage is that it's a macro that expands to all these best practice conventions that I was learning over time. And it just packages it up in a way that I can fix the macro without having to fix all the uses of the macro. That the fact that it became a popular tool for others to use was entirely a surprise to me. It was only meant to satisfy that itch that I had, which has been the case of nearly all the open source projects that I've ever contributed to or worked on. There was a need that I had, something I wanted my computer to do, something I didn't find a very satisfying solution to elsewhere. I just wrote the program that did that, usually wrote it in the most minimal way necessary to satisfy that concern, and then would give it to the community and say, well, if anyone else has this same need that I do, maybe they'll find it useful too. And that would sometimes gain other people's interest, and they would contribute or offer to collaborate with me. And that's really all that I've been doing with Emacs for all those now 20 some odd years. So it's a lot of Emacs Lisp written, no C written. I've never worked on the C side of Emacs, so haven't gone down deep into that level, but I love working in Lisp. I've always enjoyed Lisp. It's a beautiful language to work in, and Emacs provides an amazing editing environment for manipulating and writing Lisp code. The way you can navigate, move things around, cut and paste, it just works so fluidly in Emacs that it's a very fun way to manipulate syntax.
What are your other experiences dealing with the community in Emacs?
Well, after I was just contributing externally to Emacs for a long time, I was also on the Emacs Devel list where all the main contributors are, both people who write software for Emacs and people who work on Emacs itself. And there have been a succession of maintainers throughout all of this time. Richard Stallman himself was a maintainer for Emacs for a long time, and then it went to other people when he was unable to continue in that role. And at one point, Emacs lost its last maintainer. I forget who it was at the time, but they sort of resigned from maintaining Emacs, and no one had been picked yet to take up that mantle. And there were different people on the Devel mailing list saying, oh, it should be this person, should be this person. And I said, well, I would be willing to do it. And enough people were in support of that based on the prior work that I had done on Emacs that then Stallman asked me, would I be willing to do that? I said, sure. I still did not work on the C side of Emacs, though. There are a lot of contributors to Emacs, and all of the C work was always done by other people. What I did to help the project during this sort of interregnum period was I helped facilitate discussion in the community. So there was a lot of contention around certain issues. Threading was one of them. Whether Emacs should move more towards being WYSIWYG, like an editor, because that was something Stallman had voiced support for. There were a few issues that became contentious enough that there were even forks threatened, and people saying that they were going to leave the community and create their own Emacs. So that gives you a sense of sort of what the environment was like at the time. So my effort was just to try and get everybody to see the value in each other and how the strength of that community comes from everybody working together. And there were always certain individuals who stood out as spending much, much more of their time and effort. And one of those was Eli Zaretsky. He's a stalwart contributor to Emacs, and he's now the lead maintainer. And so as he was working on all these bugs and all these issues and everything else, I would just encourage the community to listen to him, right? Because here's somebody who's spending all of this time. Value that. Like, realize how much that is giving a foundation and a basis to this editor continuing on into the future. You may not agree with everything that he says or everything that he does, but he's just this force of nature moving the editor forward in time. And he's done amazing things like getting us to full Cairo support, for example, and a lot of other things that he has done. He kept the MS-DOS port alive for the longest time. I believe it was him that was doing that. So over time, I was asking him, hey, would you like to be the co-maintainer? And he told me, no, I would prefer not to. I just want to be an individual contributor. But after enough prompting and instigation, he did finally accept to be co-maintainer. And then I quickly just sort of shrunk and retreated into the darkness as his light kept shining brighter and brighter. And I feel like that was the main contribution I offered to the Emacs community, was not in terms of code, was just in getting people to value and have Eli take this position that rightfully he always was in, of being such a stalwart and foundational contributor to the community.
Oh, that's a great story. Thank you for your hard work. Many of our listeners are, still very young in their careers. Would you have any advice for contributing on the open source? Because I'm talking on my own experience. Sometimes it's very daunting to come in a code base. You open GitHub and you have this code base that you are really interested in, and you would really like to contribute, but there are just so many lines of code. There's so much stuff that you have to just compile the code. Sometimes is a huge task and it's very hard. Mm-hmm. So what advices would you have?
I would say that if the project you really like is that big, I mean, of course, looking for a smaller project is one way to overcome that problem. Also, always seek a project that you actually want to use, that you're going to actively be you're actively going to benefit from your own involvement. That's important because it makes the reinforcement cycle very natural. Everything that you contribute improves the product that you use, which makes you want to contribute more. But if it's a big project that you're set on becoming a part of and you don't know where to start, improve the documentation is the first thing that you can do. And it's usually the person who's coming into the project with new eyes who has the best read on which parts of the documentation could be improved. So you actually are in a better position than someone who knows more about the project, just because you're seeing it with that newcomer's eyes. Another one is a lot of projects have huge bug backlogs and not enough time to go through and vet them all. So just picking some bugs out of the backlog and confirming that they're still bugs, or finding the reproducible case if one wasn't provided, or reducing the reproducible case if one was provided. That's very much appreciated. And in doing that work, you will become familiar with the part of the project that bug affects. Writing new tests and contributing tests is also another thing that's very valuable. And I say this also as a open source project maintainer, what people have done for my projects that I found the most valuable, because those are all jobs that are very important and need to happen, but they're often not in the main path of interest of the people doing coding work on that project. And then you evolve to the point where you want to now contribute actual code to the project. Just pick small features. Like just always try to reduce what you're doing down to the most digestible thing that you can. If you're going to make a change that into the AST of a compiler that
Oof.
requires refactoring every single module throughout the front end and the back end, don't do that, right? Because that's a Herculean task sometimes. Even the expert on the project doesn't want to do that.
Yeah.
But if you're just making a tiny little change to the way that an error message is printed out when a template instantiation fails, everybody will love you for that. And it is very small and contained and easy to review. So I think once you start there and you build confidence, you get to know the community, you begin to dialogue with the other developers, you have some familiarity, you kind of start to feel like you're part of the project. That will naturally inspire further and deeper collaboration.
Well, that was a very in-depth advice. Thank you. Now, I think one last question, if I'm not forgetting anything, is that at the very beginning, you said that you kind of regret that you didn't give yourself enough time to go into the more academic side of computer science. Why is that?
Well, I didn't see it. I didn't know it existed. I didn't know what lambda calculus was until Haskell. And the way that I was introduced to math in high school, I loved geometry, but everything outside of geometry, I just was never any good at. Like making the numbers work out on different equations was always a source of frustration and just not a very pleasant exercise. Whereas now, math has me entranced. Like I love abstract algebra, and I'm fanatical about category theory. I love higher math, but none of that was presented to me when I was in high school, and certainly no one ever suggested to me that math and computer programming have any relationship whatsoever. I mean, other than the fact that computers use numbers, that was about the only connection to math that I was aware of. So when I went into college, I thought computer science was programming. And now I learned that you can do an enormous amount of computer science without the use of any language whatsoever. You can be working at the level of math. You could be doing specifications of your algorithms in set theory. And in Coq, you actually can do that. You can actually use real mathematical sets to specify the behavior of an algorithm that you're designing. And then you can take your implementation, which is in a functional language, and prove that it actually is an instance of that specification, which is amazing and beautiful stuff. But way back then, I had no idea that such a realm even existed. So thinking that computer science was just programming and realizing that, well, I already do programming and I have a lot of fun doing the kind of programming that I do and I can get paid for doing the programming I want to do. Why am I going to go to school for a whole bunch of years and just read textbooks and do homework? And I was always having to do like the little sample toy programs that the professor would come up with.
Yeah.
I don't want to like rotate squares or like draw pictures on canvases. That's like not what I want to do. I want to work on a compiler. I want to work on a language interpreter or something like that. Now, of course, in the 300 series classes, you
Yes.
do some of those things. So what I started doing at my university is I asked the professors, can I test out? I just want to get to those classes, right? I want to test all the way. So I started testing out, and I tested out of the first 2 years. And then I reached a professor in the third year who he took my appointment. He asked me a couple questions about data structures and he said, no, I won't let you test out. And it was just my pride at the time. I got very frustrated by that. I felt like he wasn't even giving me the chance to take the test.
Yeah.
And I said, well, screw this. I'll just do the programming that I know I love. And then I'll switch my education over to philosophy, which I also love. But I missed getting to the point. I don't even think the compiler classes would have given it to me. I needed the class where it would have introduced me to lambda calculus and how what I call functional programming today and I do on a computer began before there were computers and was originally intended as a foundation for math itself.
I think if you have done, say, theory of computation then you would start having a glimpse of what is
Oh yeah.
math and computer science and why they're actually the same in a sense, right?
Yeah.
I think when I was doing when I was doing undergrad, I was a little more lucky in that side than you, because we had logic of computational logic. So like doing derivation trees and all of that. I don't see that happening too much here in the US, right?
Right.
And you start getting to see more the theoretical side of computer science, which is this whole field that we are all extremely in love in, right? This is what
Yeah.
drew me particularly to all of this.
Yeah. And one of the classes I wanted to take in undergrad was symbolic logic, but it was so popular that I just couldn't get in.
But wait,
All the times I tried.
which department was it?
Philosophy department.
Oh, in the philosophy department. Yeah, the philosophy department in my university, they would the philosophy. I took some philosophy classes as well, but the professors would say that most of the philosophy people in our department would be afraid of the logic side because it was too much math, and they were interested in the humane part of philosophy. Is there anything else that we didn't have the chance to cover?
No, I can't think of anything.
Yeah. Well, John, I think that's it then. Thank you so much for coming. This was a great adventure. You took us on your own journey and how your path came along for computer science, for Haskell, for Coq, for blockchain and Affinity and Rust and Emacs. Wow, this was such an interesting experience. Thank you so much.
Thank you for having me, Pedro. And if I could make a shameless plug here, I'm always looking for people to do this stuff with me. So if you have interest or have background in Coq, formal verification, software verification, and you're interested in applying it in the blockchain space, just reach out. I would be interested to hear about what you've done and your background, and maybe we could build that formal methods team bigger.
All right. Well, I will put all of your details in the description of the post. If you got interested in anything that John said and you could see how much of a cool guy he is and would like to work with him, make sure to shoot him an email. So that's it. Thank you so much.
Thank you so much, Pedro.
What an interview. Wow. I liked it so much. John is such a passionate person. I learned so much. I hope you guys enjoyed it as much as I did. Because if you are still here by the end of this episode, nobody stays until the end like this. You're a very special person, and I have a special request for you. The podcast just completed 1 year of existence last week. I hope it got a little better compared to when it started. I feel like I got better. I'm getting this. I'm learning. But I need your feedback. What do you think would be nice to see in the show? Who would you like for me to invite? What topics do you want covered? Please leave your suggestion in the comments of the website, www.typetheoryforall.com. Leave us a DM on Twitter @ttforall, or just make a public post and tag us. And that's it. That was it for 2021. I hope you guys enjoyed it. I hope you guys stayed strong, stayed safe. And let's go 2022. Merry Christmas and Happy New Year, everyone. See you guys next time.